Okay, so hello everyone, and welcome back to our series at Optics. Uh, I know it's late, but we'll still say Happy New Year to everyone. Um, Welcome to this session on improving student understanding of energy and momentum concepts. We have today Mary Jane and Chandralekha to be our facilitators for the series for the session. Before we get into it, let me also share that we have a few more things coming up. Let's see what there. Oh, sorry. February 20th, we have also a session on the Colorado Learning Attitudes about Science Survey, the CLAS. And then March 20th, we would have a discussion of the assessment known as DIRECT. I think it's DIRECT. I forgot the acronym means something, but I forgot what it was. And then on April 17th, we'll talk about inquiry in scientific thinking, analytics, and reasoning. Okay. So for today, I'm going to let the speakers take over in a second, and then we'll have a series of questions and open discussion after that. And then at the very end, we'd like you to, if you can, also give us some feedback. So there'll be a link at the end of discussion where you can provide us with some feedback on today's session. Okay, thank you very much. And I think with that, I'm going to stop sharing and let you, Mary Jane, take over and go ahead.
Okay. Okay.
Yeah.
Okay. Can everybody see all right?
Yes.
Give me a thumbs up. All right. Thanks. So hi, my name is Dr. Mary Jane Brundage, and I'm here with my advisor from my PhD, Dr. Chandralekha Singh, and we're going to be talking about her survey that she created, the Energy and Momentum Conceptual Survey. If you'd like to take it away.
Yeah, do you want to actually change the slide, Mary
Yeah.
Jane? Thank you so much. I hope everybody is doing great. You know, it's really cold in Pennsylvania, in Pittsburgh at least at this time, over an extended period, but it's good to be inside. So I hope that we have some really great discussion. So Mary Jane told me that maybe I should start by introducing the survey and how we developed it. You know, that was done like more than 20 years ago, actually, uh, with another student, David Rosengrant, who's not here with us right now. And so basically, the goal of developing this survey was to figure out what are the kinds of difficulties students have with energy and momentum concepts, and think about curricula and pedagogies that would actually reduce these difficulties. And then, if we are using those kinds of transformed curricula to actually see whether actually student learning was improved, right? And it's a cyclic process. You have to keep, giving the survey and then evaluating whether things are actually looking better next time around. Go to the next slide. So basically, during the design of this survey, we thought about all the concepts that students should actually know about energy and momentum in both algebra-based and calculus-based introductory physics courses. And we looked at what faculty generally teach in these courses. We looked at the textbooks. And then we came up with some preliminary version of some open-ended questions. And then we also conducted some interviews with students to see what are the common difficulties they were having about different topics. Now, and then finally turned those questions into multiple choice format, right? That themselves kept getting revised as students were being interviewed. Now, one of the things about multiple choice survey is that, like if you give these kinds of questions, they're very easy to grade and administer, and you can compare student results across different universities or across your different classes. Like if you're teaching an algebra-based introductory physics, a calculus-based introductory physics, it's very easy to see what's the difference between those two classes at the beginning of the course, that's your pretest, and at the end of the course, after the students have actually learned those concepts. Notice that, this is a survey that you can also give as a pretest. That means without any instruction, because none of the, the language that we use is not something that is, not going to be understandable to students. Unlike, say, for example, some of the surveys in other topics, here it's very easy for students to actually know the words like energy and momentum, from everyday life. And that way you can actually see what are the kinds of things that they have learned from everyday life that you need to really work on. Because nothing is more important than being familiar with students' prior knowledge. What do students already know that I need to use as resource, that I need to think about carefully and build on? And some of those things could be like, students confusing energy and momentum or something like that. But the point is, like, if you know those things, then you'll think about how to actually improve student learning using your transformed curricula and pedagogies. Because saying, oh, this is a difficulty, and if you don't know as an instructor, there is no way for you to really focus on those concepts. So now the problem with multiple choice tests, as you know, is that the thought process is not revealed by the test answers alone. And that is why when we developed the survey, we really made sure we had the questions in open-ended format initially. We interviewed the students individually. We actually showed it to faculty to make sure they were okay with the wording of the questions so that, we understood that the kind of alternative conceptions that we were building into the questions, they actually corresponded to the most common difficulties that students were having with those concepts. Now, you are already like familiar with a lot of other multiple choice tests, right? So even though, yes, you will not really necessarily understand all the thought processes of your students by giving these types of multiple choice questions, you can learn a lot, and it's so easy to compare the kinds of difficulties your students are having with the national data, for example, from the papers, and think about what I can do to improve student learning in my classes so that students have better understanding of these concepts. And notice that all of the concepts in this are focused on energy and momentum. But, like there are many ways that they have been tested. So you can see how the context of the question and the fact that it's being asked in different ways affects students' learning. Because if you actually teach something only in a particular context, we all know that it's really difficult for students to transfer their learning from that situation to another situation, right? So if you do a particular example, students would really know the thing in that context, but it'll be difficult for them to actually transfer it to another context. So for example, just taking an example, not from energy and momentum, but angular momentum, right? One of the examples that we always do with students is, oh, if the ballerina puts her arms close to herself, her angular speed will increase. And when she puts it out, like it'll actually decrease because the angular momentum of the system is conserved. And then if on the test you actually see in the book, oh, this is a problem about neutron star. So it says neutron star is slowly collapsing under its own gravitational force. There are no external torques on the system. The angular speed initially is this. If the radius goes from this to this, what's the final angular speed when the radius changed from this to this? Now notice that for a student, they are like, why are you giving me an astrophysics problem in a mechanics course? This has nothing to do with your course. And you're like, oh, I gave the same question because, like in that case, I gave, what was the, thing, initial angular velocity of the ballerina and the initial, their moment of inertia initially. And then I was asking for the final one. And so how is this question different? You have to really think about the difficulty of the problem from your student's perspective, because it's really important to think about what are the students going to think about it. And obviously the context of ballerina and neutron star, they are so different. And so, in fact, that is the reason why students say that physics courses are so much harder than, say, chemistry or biology courses, because here we usually give to students like slightly different contexts, or very different contexts in terms of surface features like this ballerina and neutron star. But an expert would say, oh, it's the same thing. They'll just look at it, they're like, oh, it's identical, but it's totally different with regard to the context. And so this test also has the same questions about energy and momentum concepts being asked across different contexts so that you can see how much have students learned to generalize able to generalize across different contexts. If you don't ask students, questions across different contexts and have them work in small groups and think about why are these problems similar or why are these problems different? Like you probably have heard about those studies that Mickey Chi did, where she was saying, oh, students are grouping together problems based upon, oh, this is the neutrons, no, sorry, this is the inclined plane problem, or this is the pulley problem. And they're not really understanding that, they are actually energy problem, or they are momentum problem, or they are angular momentum problem, or they are Newton's second law problem. But why would they if we didn't give them that opportunity, right? So we should be actually asking students questions, with different surface features and having them work in small groups to think about why are these problems, how would you solve them, group them based upon that, and then have them struggle. Like you can give them neutron star problem, you can give them ballerina problem, and you can have them, do another problem where somebody is diving from a diving board and they tuck their body in or spread their arms out, and like ask them, how many somersaults are they going to make in the two cases? Which one will be less or more, and why? And after students have discussed and figured out that these questions should fall in the same category, then they have actually learned to generalize things. Now if you ask that question of angular momentum conservation in a new context, there is a chance that students will be able to figure that out. But we need to give students opportunity to think about the same concept, whether it's conservation of momentum or energy or whatever else, across different contexts, in order for them to be able to generalize it and see the applicability. Otherwise, students will say, oh no, physics is so hard compared to all the other subjects, because we didn't give them that opportunity to think across. Mary Jane, go to the next thing. Yeah, so this is a 25-item test. And as I said, we interviewed students and faculty. We showed it to faculty and got their feedback. And so, basically, these are questions that you can use, and we are perfectly fine, even if you wanted to use some of these questions in your course, not necessarily all, because they have been well developed. Okay, go to the next one. All right, yeah, and most students, struggle with questions, and especially with the ones that involve two concepts, right? And so, and also like this idea that work and energy are scalar quantity and impulse and momentum are vector quantities, even those ideas are pretty challenging for students. So I'll show you a couple of examples of the questions. Go to the next slide, Mary Jane. Yeah, like here is a question that is about energy concept, right? It's about like frictionless slide, and two people are sliding down. One person has less mass than the other one. And the question is asking, if they start from the same height and they end at the same height, who has larger speed? And the correct answer is A, both people will have the same speed at the bottom. But you can see that it's not an easy question. It's a challenging question for students. And again, students need to be given that opportunity to think about, why is it that the mass doesn't matter, right? And a lot of times, like combining the conceptual and quantitative aspect really helps students. One of the things that we saw is that if students actually are given opportunity to actually check, oh, mgh is equal to half mv squared, mass doesn't matter, and then you ask a conceptual question, then they're like, oh, in the last question, mass didn't matter. So maybe the answer to this is mass doesn't matter. But otherwise, if you don't combine a conceptual and quantitative question, this I'm calling a conceptual question, students a lot of times really struggle with these kinds of questions, as you would see from our American Journal of Physics paper on this survey. Go to the next one, Mary Jane. Okay, here I'm showing an example of a momentum question, where you have a bullet going at the same speed. And in one case, it gets lodged into a wood block. And in the other case, it actually bounces back elastically. And the question is asking in which case, in which of the following case, the block will travel faster. And the correct answer here is D for dog, the steel block, because the bullet actually bounces off from it. So it actually transfers more momentum, because momentum is a vector. I think that what is really challenging about this question, this is also an extremely difficult question, is that momentum is a vector, and that vector nature of momentum and how the momentum gets transferred to the block is extremely difficult for students. So at this point, I am going to actually pass it on to Mary Jane, who's going to talk about the rest of it.
Thank you so much, Shanjalika. So some of the things that I did, at least in my PhD, and that I worked with Shanjalika on is kind of looking at the energy and momentum concepts longitudinally. And we'll get to why this is really important in a second. But one thing that Shanjalika mentioned was that whenever we teach, it's so important that we combine both the conceptual reasoning and the quantitative, math skills and equation knowledge for students, that they have both of those as they're learning. We said the conceptual reasoning is essential for building like a robust knowledge of physics, especially since many times that conceptual reason is underemphasized from introductory to graduate level physics courses. Lots of times you get to a quiz and you just pull out your calculator and you're typing numbers into a calculator and it's all math and it's all equations. And it is that many times that concepts are kind of either skipped over or the teachers assume that the students will kind of pick them up as they go. And if students don't pick up those concepts and the conceptual reasoning and understanding, then it's going to make getting to the final answer much, much harder for them. So we said that this is especially even true in the upper level courses. Usually those upper level courses are focused on that mathematical rigor, complex numbers. And so because they don't have as much practice with this quantitative problem solving skills or this the qualitative part of the problem solving, it can make their understanding a lot less robust. And so we wanted to kind of see, do upper level students still struggle on some of these concepts, in energy and momentum, because it's these concepts that really show us how much they understand. So we decided to give this survey to introductory level calc students, or not calculus students, introductory physics students in a calc-based physics class, and then also upper level students in just their upper mechanics level class. And so we also gave them to a separate set of students in order to kind of look at the reasoning, and students would like write down the right answer or the answer they thought certain ones were, and then give their reasoning for them so that we could kind of jump in and see like, where are they struggling and why? What are those, where are they getting stuck? And are they the same for intro students? Are they the same for upper level students? So our two research questions that we looked at were on the EMCS, like the Energy Momentum Conceptual Survey. On which questions do upper level students struggle after instruction? And then are there any patterns in student responses from introductory courses to upper level students or to upper level for these questions? So we define struggling. If you're an upper level student, we would want at least 2/3 of students to get it right. We define for introductory level students that we want at least half of students to get each question right, and so we would say that a question is hard or a question is difficult or that students struggled on it if they didn't reach that threshold. So that 2/3 correct threshold is the one that we used for upper level students. And then our research question 2, what are the common difficulties of advanced students after instruction? So what were the questions that they did struggle on? What were those concepts that they were missing? So jumping into that research question 1, where we're focusing on upper level students. And I know in a lot of two-year colleges, you're maybe not getting to mechanics, that upper level mechanics course. Maybe you're just doing introductory physics. But a lot of what you're teaching in class has to have, you really want your students to have the robust understanding that's going to go past the end of the semester. And they're going to remember for the next year, right? Maybe their careers is kind of built upon this knowledge and you want them to remember it. And so just by looking at the upper level students, it's going to help us see how those introductory level students are faring in their class. So we looked at the performance of those upper level students on the Energy and Momentum Conceptual Survey. And we wanted to see, how many questions did they struggle on? Remember that we said struggling is if less than 2/3 of students got the questions correct. And it turns out that for half of the problems, upper level students struggled. So this was 13 questions that they struggled on out of the total 25 questions on the whole survey. And of those 13 questions that upper level students struggled on, we found that on 11 of those, the introductory level students also struggled on. So not just difficult for upper level students, but also difficult for introductory level students. And those last two bullet points, I'll say the last one, we said all questions in which introductory student performance was less than 50%, the upper level performance was also less than 2/3 correct. So we said once again that struggling for introductory level students, we just set our threshold at 50%, and struggling for upper level was 2/3. And so like kind of saying it forward and back, some students might understand something that other students don't. Every time that the introductory level students struggled on a question, the upper level students did as well. Now, that's not something that's statistically significant. We would have to go through very rigorously for hundreds and hundreds and hundreds and thousands, of students to see like how correct is this. But just in the data set that we had, every single question where introductory level students struggled, upper level students also struggled. So let's take a look at some of these. And I'm going to pull out those 13 questions that the upper level students struggled on. So once again, these are all the questions where the upper level students, after their course, after their instruction, right? So they've had introductory physics and they've had their upper level mechanics course. All of these questions that the upper level students did not reach 2/3% correct on. And on the far left column, we see, question 3, question 5, question 6, question 8. And you can go ahead in the chat. We put the PDF for the EMCS. If you want to take a look at them on your own time and kind of just see why, we're going to give you a couple examples here that Chandra Lake has already shown you. And I have another example to show you as well. But we looked at, here we have the introductory level post-test students. That's kind of like that first column. And that's just the percentage of students who answered that question correctly. So we can say for question 3, 61% of introductory level students answered that correct. Whenever we looked at the upper level students, then we looked at the upper level students, their pre and post-test scores, so that we could look at their normalized gain and see how that increased or decreased. And in that last column, we have the normalized gain. And the normalized gain is kind of how we look at how well their increase in scores were from pre to post test. Now, immediately, you're going to look at that column and you're going to say, oh, a couple of them are dashes. What does that mean? Those are questions where the post-test scores were actually less than the pre-test scores. Now, some of them are really, really concerning, right? Like that problem number 3, which I'll show you in just a minute, where students scored 12% lower on the post-test than they did on the pre-test. And, some of them maybe are not as different. Like if you look at question 22, where that's only a 3% difference, probably not statistically significant. But in general, there were some problems that students scored worse on after their upper level mechanics course compared to before their upper level mechanics course. Now we look at gain, and normalized gain is considered small if G is less than 0.3. And we had 4 questions where there was a small gain. Gain is considered medium if it's between 0.3 and 0.7. And we see that there was 1 question where there was a medium gain, and there were no questions where there was a large gain. So no questions where they were doing absolutely like superbly better than they were beforehand. But once again, these are just the 13 questions that the upper level students still struggled on after their instruction. And we said that whenever student pretest performance was below a certain level, it's very difficult for students to improve much, even at the upper level classical mechanics course, right? So I'm going to kind of look at one of these questions, and this was problem 3 from before. And this problem says, a moving white hockey puck collides elastically with a stationary red hockey puck on a frictionless horizontal surface. There's no net external force that's acting on the 2-puck system. And the question asks to select all the following statements that must be true for the elastic collision. And option 1 says the kinetic energy of the white puck is conserved. Same before and after. And if we were looking at something where maybe there was only one object, right? We might say that kinetic energy is conserved a lot, right? It's an elastic collision, but we would have to consider all objects. And so if we only have the white puck, we cannot say that number 1 is correct. Option 2 says the linear momentum of the white puck is conserved. not quite correct, right? We would have to once again look at the whole system, right? Linear momentum is conserved in the whole system and not just in one singular object. And then number 3, the linear momentum of the two-puck system is conserved. 3 is the only one that is correct here. So option B is the one that we want to look at. And so I'm going to show you how the students, like how their answers splayed out. So whenever we look at the upper level students, these are their pre and their post-test scores. So we can see 1% of students thought that A was correct pre-test and no students thought that it was A post-test. The correct answer was B, right? That number 3 is the only one that's correct above. And we saw that there was a 12% decrease in that correctness. But what we see is that there was an increase in option D. And technically option E, there was not quite an increase, but a lot of people also chose D. And so D said that 1 and 3 were correct. So they're thinking that option 1 is correct, that the kinetic energy of the white puck is conserved. And that can kind of be misleading because lots of times we say, oh, it's an elastic collision. That means that kinetic energy is conserved. But it doesn't mean that kinetic energy is just conserved with one singular object. It means over the whole system of objects that we're looking at. If we compare that then to the introductory level post-test scores, we can see that the introductory level students were about on par as they were right at the end of their class to whenever they go and start their upper level mechanics course, that pre-test in the upper level, they had about the same score, that 61 to 65%. But then after their whole entire class, that score went down by about 12%. So we can already see that without giving students kind of that scaffolding of teaching those really robust conceptual knowledge, the students can really suffer for that. And so it's really important to kind of combine that conceptual knowledge or that qualitative knowledge with that quantitative knowledge. So overall, some student reasoning often focused on elastic collisions, meaning kinetic energy is conserved without paying attention to knowing that it's for a whole system rather than just one single object. And by the way, anything that you see in quotes here are direct student quotations from kind of whenever we ask them to explain their reasonings. Bullet 2 says, for all collisions, momentum must be conserved for all particles in a system, and by definition, elastic collision means kinetic energy is conserved. So once again, this student is an example of one of the students who chose answer option D, where they thought that the kinetic energy was conserved for just one of the objects. And so they're using a lot of the correct language, but they're just incorrectly thinking one object versus the whole object. Another student said elastic collision implies that kinetic energy is conserved. No net external forces means that dp dt is 0. And another student said in elastic collisions, the kinetic energy is conserved. Linear momentum of a system, both white and red, is conserved. But once again, they were saying all the correct words, but then they chose an answer option that said that like the either momentum or the kinetic energy of just one object was conserved. So to kind of conclude this portion, we said that many of these upper level students were struggling with introductory level material, right? We didn't take the test and we didn't change it to make it more appropriate for upper level students. The survey was still created for introductory level students with introductory level concepts, but just whenever we gave it to upper level students, many times their scores really dipped compared to after they took that class at the introductory level. And right, that could have been because maybe they learned something incorrectly in that upper level mechanics course, or more likely than not, maybe just because they didn't see that concept, maybe they weren't tested on that concept. They didn't have to study the concepts as much as they had to study the mathematically rigorous problems, right? With numbers and using equations and calculators. And so because they didn't have that focus on the conceptual understanding, maybe, if you don't use it, you lose it. We saw that if the introductory level student performance was less than 50%, the upper level student performance was also less than 67 or 2/3% correct, which is kind of interesting because it gives us that kind of foreshadowing of, oh, if I give my students a survey and I can see that they do less than 50% correct, that means if I don't do something as the instructor, they're not going to get it at the end of their next class, right? And so it gives us the opportunity to kind of see in advance what they're struggling on to see where we can help scaffold their knowledge for the future. And we said that it's important to integrate both conceptual and qualitative aspects of mechanics, even into upper level physics classes, where a lot of times maybe professors may be more focused on the math and less on the concepts. And that is all that we have, or that I have for you today.
Mary Jane, we have a question in the chat.
Okay.
Anthony asked if the student quotes were from the upper level classes or from both the intro and the upper level.
These are from the upper level classes.
Okay.
Good question. Yes, because we would, especially like with the DPDT, right? That's definitely the upper level class.
Thank you.
And that upper level class was therefore a mechanics, physics. So these were all physics majors then in a mechanics course. Yeah. Okay.
Yes.
Oh,
Yes.
very interesting. Was that the one question where you had the most significant dip, or were there other which is there like a theme about this dip? Does it occur in particular topics, or do you have?
A lot, that's a great question. A lot of the topics that we did see students struggling with was that idea that recognizing that the one that we showed you here today is that yes, whenever we say that kinetic energy is conserved, or if we say that momentum is conserved, it's conserved for a whole system and not just one individual topic. Some of the other questions, and by the way, you are absolutely free to kind of look at the table and like maybe go through the survey and look at some of those questions. But some of the other common themes is recognizing that total momentum can be zero, even if different objects are moving, right? And so like there's one question on the survey where it's like you have a plate and you hold it above the ground and you drop it, and then it kind of moves across and horizontally across the floor, right? And so whenever you drop it, at least, if you're looking at a top-down view, it does not have any momentum, but once it hits, it kind of spreads out. And so pieces fly in different directions. And those different directions, if you add up all of their momentum, it adds up to zero. So before and after that momentum is zero, the students aren't recognizing that things can move, but the total momentum be zero.
Okay. And here I see Brian making a comment about the fact that students have I guess, a difficulty with the whole system thinking as opposed to object thinking. He says they think they make the system smaller, only one or two objects in collision, they will simplify the problem, and they don't choose an appropriate system for that. So is this something we could extrapolate to other situations, this whole notion of thinking at the one particle thing versus a system? Is this something that can be a little that is also affecting other ways of doing problems in physics for students, I mean, as a challenge?
Oh, absolutely. Even if it's, I mean, like I see this sometimes with my students whenever we're learning about forces, right? Lots of times if they're not thinking about everything that's included in a system, they might miss a force, right? Or like they might miss a contact force here or there.
Yeah.
I know that I see it a lot in energy and momentum as well. Chandraleka, if you see it as well.
Yeah, absolutely.
So are there ways so what kind of intervention would be appropriate for this? I mean, ahead of or in the course, are there any particular approaches that you find preferable to others in terms of teaching those conceptual dimensions?
I find it really helpful to remind myself that I also have to test these conceptual understandings, right? Like if I'm going to give my students an exam at the end of a section, I don't want to just put on number problems. I have to put on conceptual questions as well. And yes, you can do conceptual questions right, you can take questions directly from the survey. You could put them on an exam. You could, change them up. But just recognizing that, yes, you do have to use them. You do have to kind of quiz on it for students to recognize it's important, because students are going to look at, like what problems did we do in class? What problems did we do on the homework? What problems were the quizzes on? And then that's how they inform themselves on how to study for an exam. And so if they don't see any sort of conceptual problems, then they might think that they don't need to study it at all. So just kind of like going through, and you can always build up these conceptual problems, even from the introductory classes. Lots of times in the book, there's a lot of conceptual problems. Depending on which book you use, lots of times books will have conceptual problems at the end and quantitative, more problem-solving problems at the end of a chapter. And so there's definitely a lot of places that you can find them.
So
Anthony, I'm
sorry,
sorry.
just a second. I was just going, just a second, Kenny. I just wanted to, Kareem, add to Mary Jane's thing that I do agree that students will really focus on what they are tested on. So if assessment actually includes conceptual things for grade, I think that their incentive to actually focus on concepts and integrate it with all the other things that they are learning will be more. So that's a really good thing. And like I was saying, the two approaches that I really like in my own classes, and I can actually send you all like some papers that we've written on, say, categorization of problems, right? I mean, so if you give a whole bunch of conceptual questions on energy and momentum and they're all jumbled up, or it's a whole bunch of things, some of it is Newton's second law, some of it is conservation of energy, some of it is, work energy theorem, some of it is a momentum conservation or, a full impulse momentum theorem, then, if you say to students, work in small groups to try to actually group together problems based upon how you would solve it in small groups, and you reward students for those kinds of things. And maybe in the test also, like you can give them some points for actually grouping together problems based upon how they have how you would solve those problems. So it shouldn't be these are inclined plane problems, because maybe one of those inclined plane problems can be solved using one principle of physics better than the other one, right? So you can say, which of these problems can be solved in similar ways most, effectively. I think that those kinds of exercises done in small groups, because students can learn so much from each other. I mean, my own research shows that students should be actually given opportunities to work with other students, because they can actually understand each other's difficulty better. They can actually help each other much better, because they understand the prior knowledge of other students. So this is an approach that I would strongly recommend, that give them conceptual questions and have them actually group them based upon how you would solve it. Then they'll realize, no, these are not spring problem and pulley problem and inclined plane problem. These are problems involving certain principles. The second thing that I really actually think is very important is that when you are doing conceptual questions, combine them with quantitative problems, because otherwise, oftentimes students think that I need to guess here. If you give this question about like, a person with a greater mass and smaller mass, sliding down the same slide, starting from the same height, ending up at the same height, people are like, oh my gosh, I must have to guess the answer here. And they should realize, no, this is not a guessing task. This is actually the same thing that you've just learned. So give them a problem that first says, somebody is going down a thing, they were initially at this, they came to this final speed, what would be the final speed at the bottom? Now they have actually worked in small groups to say, oh, mgh is equal to half mv square, m canceled out, so speed is, not dependent on mass. Now, if the next question is like that, and you'll see that the energy and momentum conceptual survey actually has several questions that are like that, where something is happening from some same initial height and then going to the same final height. And students are really confused about those kinds of problems, depending upon the context and how familiar they are with that context in their class. And so I think that combining quantitative and conceptual questions, giving them back to back, what I mean is that giving them one after the other will help students understand, oh, this mg is equal to half mv square, and the mass canceling out is related to the mass not being an important thing in figuring out what is the speed of the person at the bottom. So I would say use that approach also. Thank you.
Thanks. Anthony, you had your hand up earlier, so do you still have?
Oh, yeah, maybe it's more like a general, like a concept inventory question. So maybe I had like an out or maybe misunderstanding about, if a question was on a concept inventory, like it should not be used for like for evaluation, right? Like you shouldn't take it and put it like on a quiz or an exam. But I think it was mentioned both times that that's something that you feel is okay. So I'm just wondering, like, was my understanding maybe like maybe a misunderstanding, or is it maybe like author dependent in terms of like how you might use a concept inventory like outside like the maybe prescribed pre-test, post-test?
Yeah, I think that this is, a really great question, Anthony, and different people have different opinions about it. I am saying that so long as you're not handing over the entire, survey, concept inventory to the student, and because in that case, it'll show up somewhere on the web, right? I
Mhm.
think that it's okay at least for our test, not for other people's. I'm not going to take responsibility for other people. And in fact, Tom is here, and like I have used his survey, like energy and momentum conceptual survey, and I've asked him the same question, is it okay? And the point is like, I think different people have different opinions, but in my class, in my opinion, if you are just using it as a learning tool for students, let's say that you use this particular question that is shown here and combined it with a quantitative problem, right? And had the students actually work on it with in the class with other people thinking about what's the answer to this. And then they realized, oh yeah, when I actually did the quantitative thing, mgh is equal to half mv square, m doesn't really matter because it cancels out. So here the math shouldn't matter. You have actually really helped use this question, which was actually developed after so much effort using the language that actually is understandable to students and that actually is agreeable to a lot of faculty that we iterated it with. I think that we are perfectly fine having faculty use it for that purpose.
All right.
Thank you.
Thank you. Anybody else has a question for facilitators today? Something you want to, or even just a comment or observation or something you want to share from your own classes, things that you do on the same topic? Okay. A quick technical question. How much time do you allocate for the survey?
So I would say that they should be given at least 40 minutes. If you look at Physport, we say 50. 50 is the typical class period. So I think that I like to give the entire time that you have in a particular class because I don't feel like people should actually race.
Mhm.
And so they should have the opportunity to think. So
Okay.
this quote will say like something like 50, I think, if I remember correctly,
Mhm.
even though majority of students will definitely finish this in 40 minutes, but I don't want to actually
Yeah.
disadvantage people who are slow, but because, people are doing deep thinking and it takes time.
And in terms of scheduling, do you think it's a good idea to give the survey at the beginning of the semester, or is it better to wait until like whenever the semester is about to get into the topic of energy momentum, let's say typically after Newton's laws, or does that make any difference at all?
I don't have any preference. So, whenever you feel is the best time, you can actually give it. But like for example at University of Pittsburgh, our institution, typically it's always in the first week and then sometime later after the concepts have been covered, but that is mostly because the first recitation, the teaching assistant, for example, in introductory physics, doesn't necessarily have anything else to do, because they're just saying hi. And
Yeah.
that's a good time to actually evaluate what is the pre-knowledge that students have coming in,
Yeah.
because I mean I cannot emphasize the importance of being in the zone of proximal development of students, right, as Vygotsky said. So you really need to make sure that you're building on that prior knowledge. So what do students know? And so the pretest actually should be something that you should be looking at carefully to see how are my students answering these questions so that what are the common difficulties that they are going to that they have, so that I can actually address those things. So we do it very early, and that actually also works out well for people to actually think carefully about what are the kinds of difficulties students have and how do I need to design instruction to think about them in a meaningful way.
Anthony, go ahead, and thank you. You have your hand up.
Yeah, so, sorry, just something that occurred to me. We're thinking down the line of talking about how like to your college faculty could do kind of like alternative ways of making sense of assessment data. And since you captured that student reasoning part, was that through like student like interviews, like face-to-face interviews? And I guess is it, if do you see a way of like getting that student reasoning that maybe not be wouldn't be so like labor intensive for like a tier college faculty to do? Sorry if that's a kind of basic PR question.
Yeah, I can answer that. So one way that you can do that is you can take whatever survey you want to use and you can administer it to them online as like a Qualtrics survey or just like a Google Forms survey and, explain your answering, explain your work, explain your reasoning after that. And then all of that, whatever they type in, it's quick for them to type and it's quick for you to read and you don't have to try to like parse through their handwriting. That can be really quick to do. And to just kind of like export that data, whether it's like a Google or sorry, like whether you're using Excel or some other program to just kind of like look at a glance, and because it's online, you can sort it, of all the people who chose A, what was their reasoning? Of all the people who chose B, what was their reasoning? And so I mean, I like Excel. Excel is my personal favorite, but you can always, just administer online and then use a computer program to kind of group different thoughts together, different answers together.
So when you see results about student reasoning, it doesn't necessarily need to be like a face-to-face like
Correct.
discussion. Right. Okay, cool. Thank you.
Yeah, and one of the great things I would say about physics is that even though students have difficulties, the difficulties can be classified in a few categories. So if some student is thinking that a huge trailer truck, when it hits a small car, will exert a larger force, that is not going to be like some straight thing. That will be a common difficulty across many students. So related to a particular question, like the kinds of things that people gravitate towards when they are actually using their intuitive knowledge, is very similar. And that is a good thing for us as instructors. So I would also say that, Anthony, that it also helps in addition to that. So yes, definitely listen to your students, right? Give them the opportunity to discuss things and, have these kinds of discourses in your classes. But looking at the literature in physics education research, for example, if you look at our paper from, I don't remember which year it was, but it could be like 2005 or something, the American Journal of Physics paper on energy and momentum conceptual survey development, we also talk about what we found in our interviews. And I can bet you that almost all of those kinds of things are going to resonate with you if you have taught your own courses for a long time, even though, you are at a different institution. So I'm just saying that, the percentage of students who have difficulties across different universities varies a lot, right? I mean, so I can say, oh, X% were having difficulty. You may find it's totally different. But the kinds of difficulties they are having, oftentimes, like they turn out to be very similar because the types of difficulties are very similar. And that's why, the kinds of curricula and pedagogies that would help students, they are going to be also along the same lines, although you do have to adapt it to your students, right? I mean, like, students may have different types of self-efficacy and other, types of issues and somewhat different prior knowledge. And so you need to actually think about how you can actually take advantage of students' prior knowledge and build on it in a meaningful way. But what I'm saying is that related to a particular topic, like, for example, for this question, students would actually have similar kinds of difficulties, even though the percentage could actually vary, right, across different schools, because the student difficulties about what people think intuitively are similar. I hope that makes sense, kind of.
Got another question for you. Maybe I don't know how related it is, but do you see any relationship between the FCI and this energy and momentum? Are there any patterns about the responses of students or the difficulties that the students are experiencing in both?
Sorry, can you actually clarify one more time?
So what I was thinking about is any kind of relationship or correlations between students' responses to the FCI, Force Concept Inventory, and the Energy and Momentum Survey. Are there connections between the way the students are struggling with one type of question on one survey and the other types of questions on a different survey? Are there any?
That is a really great question. And I don't think that I have specifically actually looked at that. I mean, so you are saying the same student, right? If you
Yeah. Same student.
correlate the same
Right.
student
Yeah, if we could.
across different questions, like are there difficulties related to force concepts versus energy and momentum concepts? How
Right.
are they correlated? That is
Yeah.
a really, really great question, Karim. And I don't believe that I've seen anybody necessarily looking at that kind of correlation, although that would be awesome.
So that was me, my next PhD in PR then.
Absolutely.
All right. Let's see, anything else anyone else would like to ask?
There's just a technical question about the passcode. Kai said that they couldn't open the document. Oh, I see Mary Jane has responded.
Yeah, sorry, if you don't need Adobe to open it, but if you have some sort of other PDF viewer, I know on a Mac, lots of times I'll use Preview. That will work. That's like where I view my PDFs. And so like if you have downloaded the file, you can right click it, open as, and then if you have whatever different program you have to view the PDF, that should work.
Okay, so let's see. Maybe maybe I can at this point consider sharing the link for the feedback. Chris, do you have it, or should I do it here?
Well, thank you so much for having us. Thanks a lot.
All right, so let me see. Let me
And if you all have any questions, when you think about administering it, we would be happy. Mary Jane and I would be both happy to discuss it.
Okay, let me see.
Yeah, and
Thanks.
yes, thank you so much for having us today.
Okay, so let me.
Yeah.
Oh, yeah. This is okay. So anyway, yeah, thank you very much for joining us today, and I think we still have a little bit of time. So if you have any, okay. So thank you from Anne. Anybody else has any comments at the end? Otherwise, we'll thank our speakers one more time and hope to see you again. Remember, we have more talks coming up this semester for the PR interest group at Optics. I'm sorry, what's the official name of the event? Oh, you mean this event? Yeah, so this was let's see, we called it Energy Conservation. Let's see, what is it? Let's see here. Let me bring it back here.
We could just say EMCS.
EMCS.
That's good enough.
Yeah, EMCS 20. Oh, that's for the survey. I'm sorry. Yes,
Yeah.
that's right. Okay, I forgot that little detail.